A and B are attached to the ends of a light string. They're on this slope. Let's start getting some forces down as we go. This is going to be 2 mg, the weight experienced by A. And here on B, it's going to experience its weight of 3 mg. There's going to be a normal reaction, so I'm going to add that in now. Sometimes I forget to do that. And I'll leave everything else for the moment to keep reading through. So A is held at rest on a rough horizontal plane, so there's going to be some friction going on. And it's inclined at angle alpha to the horizontal, where tan alpha is 5/12. So 5/12 here. Draw a little triangle and let's work out the exact values of sine alpha and cos alpha. This is a 13. It's a 5/12, 13 Pythagorean triple, but of course you can do 12 squared plus 5 squared square rooted to get that 13. And then sine alpha is 5/13. Cos alpha is 12/13. String passes over a smooth pulley, and we can work in 2 dimensions. Essentially, that's then. Okay, and then the coefficient of friction is 2/3. Blocks are released from rest with the string taut, and A moves up the plane. So that is going to mean that there's a friction acting down the plane to oppose motion. And the tension after the block's released is T, so it's going to be pulled up the plane by capital T, and then there's going to be another tension here that's stopping B from just falling due to gravity. It's going to experience through the tension like the effect of 2m, the mass, the A. Okay, and then the blocks are models of particles, the strings models being inextensible, and we're asked to show that capital T is 12 mg. Well, I'm going to get, this is an 8 marker, by the way, so you can see there's going to be quite a few steps. The connected particles question, we're going to look at A and B separately, but then combine them through the fact that the tension is involved in both. So if we look at B, I'm going to apply F equals ma down, because it's moving down. So 3 mg minus capital T is going to equal 3 ma. And then I'll also look at A, which is moving up the slope. So I've got F equals ma up the slope, T minus Fr. Right, now I've got to look at the component of the weight. I probably should have added that at the very beginning. So the weight's acting down. There's going to be a component acting perpendicular to the slope and a component acting parallel to the slope. I want the parallel one here. So it's actually opposite the angle. It's going to be sine alpha, 2 mg sine alpha. And then that is going to equal 2ma. Of course, there's still a lot to do. We haven't worked out what Fr is. I haven't substituted into sine alpha, but I'm just going with that bit. I just want to very quickly talk about that again. This is something that sometimes people get confused by. I'm just going to draw a bigger triangle over here. So this is essentially my hypotenuse. This is my main force, and then I'm splitting it into these two parts. Here's my right angle. And you can see if I call this, oh yeah, and this angle's alpha. If I call this question mark, then we can see that sine alpha is equal to question mark over 2mg. So we just rearrange it and we can see that question mark is then 2mg sine alpha. And that's where I went straight into. And then if I did the same over here, this one here would be 2mg cos alpha. So that is a little very quick explanation using right angle triangles. But the idea, well, what you really want to be doing is realizing you're splitting it into components and then just working out, do I want the opposite or the adjacent, and then times by either sine or cos. So let's keep going. We know, because it's moving, that Fr is going to equal mu r. Now I know what mu is, I just don't know what r is at the moment. So I now need to look at the forces perpendicular. Sorry if I'm going a bit all over the place here. But yeah, I'm going to resolve forces perpendicularly. There's no resultant force, which means that r is going to equal 2mg cos alpha, as I was talking about before. And now I'm going to sub in for cos alpha, so it'll be 24 mg over 13. And then that means Fr is going to be 2/3 of that, which ends up giving me 16 mg over 13. Okay, I'm well on my way now, because what I'm going to get for A is that T minus 16 over 13 mg minus 2mg times sine alpha. That's going to be 10 over 13 mg is equal to 2ma. Let me just write both equations down. So I've got my 3mg minus t equals 3ma. Remember, that was the equation of motion for A. And I just need to tidy this second one up. I'm going to get minus 26 over 13. Hey, actually, that just becomes 2. So minus 2mg is equal to 2ma. Amazing. And now we add them together. Always do this. This will always happen. The tensions will be acting in, like one will be plus and one will be minus. So I'm going to get mg is equal to 5ma. Cancel out the m's. That means that a is equal to a fifth of g. We're nearly there. Now I just substitute back in. I'll substitute back into this one. So t is going to equal 2m times 1/5 g plus 2mg. And that ends up being 2/5 plus 10 over 5 mg. We do get our 12 mg over 5. Good work. Let me just summarize what we just did because there was a lot going on there. We worked on the equation of motion for B. I'd always do that one first because there's a lot less going on. And then we looked at A, loads more to consider. So although I didn't do it straight away, at one point I equated R with the component of 2mg acting perpendicular to the plane to work out what that is. And that helped me work out friction using the coefficient of friction. And then we could write down the equation of motion for A. So it was T minus the frictional force minus the component of the weight acting down the plane, and that equaled 2ma. We had then, or actually, then it came together really nicely, got rid of the fractions, added them together, worked out what A was, substituted back in, and that got us T. Now told that after B reaches the ground, A continues to move up the plane until it comes to rest before reaching P. There's not going to be any tension anymore. So once B hits the ground, this goes, and the only forces acting on A, well, it's got the normal reaction, it's got obviously the weight, but it's also going to be the friction, and the weight and the friction are going to cause it to stop, to slow, decelerate, and then stop. Now the question is here, does it actually then start going down the slope? So what is going to happen after it stops, or after B hits the ground, in fact, is that there's still going to be a component of weight here, which is going to be 2mg. Sorry, that is the weight, and then there's going to be a component acting down the slope. We've still got our normal reaction, which is actually going to be exactly the same. So I think it was 24 over 13 mg. Now friction is going to be going in the opposite direction. And we've got the component of the weight acting down the slope is 2mg. Then remember, it's this bit here, so it's sine alpha. I've got this above. I think I already worked out that it was 10 over 13 mg. And then this time, Fr is going to be less than or equal to, because we don't know if it's in limiting equilibrium, it's not moving, but it's going to be less than or equal to that value that I found before, which was 16 mg over 13. Okay, so the point is that there's a component of the weight trying to make it go down the slope, but it's 10 over 13 mg, and there's a frictional force opposing it, and that friction, the maximum frictional force is greater than the component of the weight. So I can write down that 10 over 13 mg is less than 16 over 13 mg. So friction will overcome component of weight, and therefore it's going to remain at rest. Hey, brilliant. Yeah, I like that question. Then finally, suggest two refinements to the model that would make it more realistic. I just went with air resistance, and I said A and B, we could give them dimensions instead of modeling them as particles. You got a whole host of things you could say. You could talk about weight of the string, extensible string, friction at the pulley, dimensions of the blocks, or it just says allow for. I think that's absolutely fine. Do not model blocks as particles. Include air resistance. Include rotational effects of forces on blocks, i.e. spin. You can't say things like use a better value of gravity because we've worked in terms of g, and actually it's independent of that. So yeah, those are some things you could write down. Well done.